So actually today is the session on the no ladder estimator of H0, and lensing is one. We'll hear more of type 2 supernovae later, a bit of maser. Let's see. But so the idea is to see what probes we can use without building a ladder, and if possible, independent of any other probe. So lensing is one of those. It has, of course, its own drawbacks. So we'll go through these and see how we can mitigate these drawbacks. So it's all about observing lenses. That's a lens quasar you see on the upper left corner. The light curves of these quasars or quasar images, and the tools we use or we will be using in the future to obtain these data. And then once you measure the time delays for time delay cosmography, you essentially have to fit a model to your lens galaxy, a mass model, and turn the delays into H0. So I will show you how we do this. If I can pass the slides. Okay, so time delays. So here you have an observer, a source, in this case a quasar, it can be a supernova, and the source has different images. So you'd never see the source, you see only the lensed images of the source. You have optical path from the observer to the source, and they are different in length. And because of this, if you have a signal emitted by the source, you will see it at different times at the observer's position. So there is a time delay due to geometry. But it's not the only one, unfortunately, because the time delay also comes from the potential well of the lensing galaxy that is probed at different places along the two lensed images, well, two lensed images in this case, 4 in many cases. So you have a geometric time delay due to the difference in length between the optical path, and you have a gravitational time delay due to the potential well of the lensing galaxy. And that's why you need to reconstruct this potential well to turn your delay into H0. Now, how the method works, so it's not new, it was invented in '64 for lens supernovae, by the way, and it was before quasars were even discovered, but it was applied to lens quasars in the first place. Because lens quasars are variable sources, they're continuously varying in some erratic way, so you can measure delays with this. So the idea is, if you live, in a schematic way, if you live in a big universe, then the time delays are bigger, H0 is shorter. I will show in the equation why. And it's the opposite if you are in a smaller universe. So how does it work? So the time delay depends on the redshift of the lensing galaxy that we can measure. It's hard, but you can do it. It depends on the source position that you don't have. It's a free parameter because you never see the source position. It's lensed. You cannot unlens the quasar. It depends on the lensed images. So every pixel of your, let's say, HST or James Webb image of your lens is measured by this. And it depends on the potential of the lens at the position of the lensed images. So the quantity you're after to turn the delays into H0 is the potential at the position of the quasar images, not necessarily the potential everywhere. So the idea is you measure this, you have nice imaging, you have a nice model, hopefully. And what you measure, in fact, is this quantity. So what you measure is a ratio of distances. You don't measure H0 directly. So the measurement is a bit like in BAO. You measure D times R. Here you measure a ratio of distances. So the good thing that this is a single-step method, so no calibration, no anchor, no nothing, no on the CMB, on supernovae, whatever. It's independent of any other method. We never use CMB to constrain our lens models. We never use any supernova to constrain the H0 results. You can still combine if you want, but you don't have to. So it's completely independent, single step, but it has this psi, and in fact, the whole game now is about measuring this psi. So just for information, there have been a number of programs running. So I started in 2004 with CosmoGrail. That was supposed to do time delays and models, H0 and so on. It was way more complicated than we thought, of course. So we measured essentially the delays here. And that was already hard. Then came Holy Cow, led by Sherry Suyu. So it's H0 lenses in CosmoGrail's Wellspring. So once Cosmography was successful in measuring delays, we used the models of Sherry-Suyu at that time and started to do H0 estimates. Now the collaboration grew. There have been different collaborations. It was maybe not a mess, but it was going to be a mess. So we grouped everything in one single collaboration that now has a simple acronym, time delay cosmography, so TD Cosmo. So all our papers now are published under this flag. Okay. Now what do you need? So you need to measure the time delays. So we'll show you how we do this. That's one of the ingredients. You need to measure the mass in the Einstein radius of your lens, and you need the mass slope, that's psi, at the image position. So the mass slope, the gradient of the mass, is the potential at the image positions. Now, it's not the only ingredient. You also need to account for all the stuff along the line of sight. So if you have, let's say, nearby satellite next to the lens, you include this explicitly in the model. And if it's far away, like the blue lines here, you still have mass contributing to the lensing potential, and we correct for this in a statistical way. So at the moment, the main uncertainty is on the mass slope. Delays are not really anymore a problem. Actually, when I started Cosmography, I remember feedbacks of some referee was, you will never measure a single one. We have 50 now. So time delay measurements. So I like to show this slide because it starts in 2003. So I like to tell my students that while they are working for me here, I was working for them here when they were at high school. So you see, it's a long-term program. So it takes 20 years, at least in some cases, to measure time delays. You see here. So this is an HST image. It's just to mimic the fluctuations of the quasar. It's not the data we use. These are three light curves of the three bright images. Then this is the faint one here. So in fact, the delay between the three bright ones is almost zero, and you have 90 days delay between the pink, the violet curve here, and the others. And that's what we use to measure H0. Now, I showed an HST image, but that's what we actually have. This type of data, that's the same object observed from the ground every few days. That's the PSF associated to each image. That's the deconvolved version of the image. That's what we use to measure the photometry. And the deconvolved image is decomposed into point source and an extended channel. So if there is a complicated background, it's removed from the photometry. And we reach the millimagnitude at magnitude 20 with this type of software. And by the way, I would really like very much to apply this to the Cepheids and tip of the Regia and branch stuff and so on. Let's see. Just to give you an example, so I give you technical details of the method. You can go to the slides for the details, but just to give you an example of how it works or how it performs, take, for example, this object. That's a ground-based image of one of our objects. That's the deconvolution. That's the HST image. And we don't use the HST image when deconvolving. So you see this one, for example, as an edge-on lens. That's the deconvolved version, and that's the HST image. So that's the type of data we get to measure the light curves. That's a typical, not the typical light curve. That's one of the good ones. And you see the time delay, by eye. You see this plateau here is delayed by a few days. And by the way, now we measure the delays not in 20 years, but in only 1 or 2 years. How we do this is by increasing the cadence of the monitoring. So it means that you will never see LSST data of that quality, maybe in terms of depth, yes, but not in terms of sampling. And that's key because you unfortunately have microlensing. I will show you later. So microlensing makes life complicated, and you can mitigate microlensing with high cadence monitoring. So now it's just to show you the data. So we were told in 2004 that we will not measure anyone. So that's an example of 9 of the lenses we have in the last paper that is now on the web. It's been published in ANA now. So delays are not really the problems. Now we have maybe not more than enough, but enough. We even have lucky delays. I will come back on this. We thought it was a quad, so a double quasar that has 4 images. So for one of the quasars, and the second quasar would be doubly imaged. turns out that in fact, it's one single quasar that is imaged 6 times. Looks like, no, I'm not saying that for the record of the number of images per quasar, but it's great because it actually, it breaks all the degeneracies in the lens models. So that's what we call, a jackpot lens. In fact, this one is even super jackpot because it's also next to the polar star, so you can observe it all the year without any gaps in the light curves. Now, this object is just fantastic. So we didn't publish anything yet on this in terms of cosmology. But actually, these are 3 light curves, no, 4 light curves of the bright things, and these 2 light curves are the 2 faint things. And I remember when Fred Dux did the first light curve, I told him, it's strange. The images of E and F are similar to the other ones. So check your calibration, the night-to-night calibration, because there is something fishy. Because we thought it was 2 different quasars being lensed. I said, no way, that's what it is. And then he shifted the curves. And, there was a delay, that matched perfectly when you do the curve shifting. And then we also got James Webb NIRSpec spectra of this. And in fact, it turns out that this arc is not the host galaxy of this quasar. It's a second lens between the quasar and that lens, which is lensed by the first. So you have strong lensing of one lens by another, and then strong lensing of a quasar behind this, and the light goes along the first lens, across the second lens, and arrives to the observer. So we call this a zigzag lens. It was predicted a few years ago. Now it's there, it exists. And it has, in this case, 6 delays. Now, this was really hard to obtain. Now, this is, okay, each point here on these curves costs 300 euros. And you've seen many of the other ones before. Okay, anyway. So, microlensing, probably I would skip this because, yeah, I just, message to take away is, measuring the delay looks easy. The curves look alike. They are not, because you have stars in the lensing galaxy. They pass in front of the quasar images, and that introduces some flickering decorated between the quasar images. So they quite match, but they don't exactly, and that can bias your time delay estimate. And that's why you have, and this thing is very slow. It takes months or years to change. That's why you have to observe for years to mitigate the macrolensing. Or you go to very high cadence, and then you start to catch the small quasar variations, small in amplitude and fast. And there you can discriminate between what belongs to the quasar in the light curve and what belongs to the microlensing. And if you do this, you need only 1 year, if you're lucky, maybe 2 seasons to measure the delay correctly. Okay, so yeah, just to show you, these are the light curves of the object you saw before. By shifting by the correct delay, but not correcting for microlensing. And then we correct for microlensing, for example, just with a straight line across seasons or a spline. That's what we usually do. And there is a whole procedure to do this, and then we get the delays and the error bars from there, and the correlations between the delays. Okay, so that's for the delay. Now, once you have the delay, you want psi, the one quantity I showed before. So you take a lens, you take an HST image. In this case, you have the quasar images, and what you want is the slope of the mass at these positions. So that's a radial cut of the slope. This gray area is where you have lensing constraints on the potential well. And there we fit different models, a very simple one, power law, or a more complicated one, chameleon, plus Navarro, Frank, and White for the light and dark matter. Why I show this plot is because the very simple model and the more complex ones converge to the exact same value. So even though there are degeneracies in the models, it's complex models and simple model converge to the same thing, which is quite a good sign. Line of sight, I told you need to account for everything on the line of sight and correct for this. So this is the mass of the lens in some lensing units before and after correction for the line of sight. That's H naught we get before correcting for line of sight. That's after we correct for the line of sight. So we didn't plot this, made a fit to the points and correct. We correct all the points in the way we think is correct. And we apply it, and we see that the correction is, given the error bar, almost perfect. So this is not, let's say, the main contributor to the error on H0. Just to show you, if you do this for 1, 2, 3, 4, 5, 7, 6 lens, it takes time to do this. Typically that's the value you get for H0 with lensing, with simple power law models, 73, 4, plus minus 1 or 2. But I will tell you more about this. That's our sample. So actually, all these lenses agree, and all these lenses, as we say, is unhappy in its own way. Each time, we struggle with a satellite there, a double lens, a hidden image. All this gives you the same value of H0. So to me, it's already a sign. But we have the MST, so mass sheet transform or mass sheet degeneracy. So we'll show you what it is here. So the mass is kappa, the middle line. Now you can apply a correction, a transform on kappa that will change all, so that won't change any of the lensing observables, but will change the time delay. So you see the images on the right side are all the same, but you can change the source and the mass in different ways, in opposite directions, and you change nothing of the lensing observables. So that's a problem, because you change the mass and you don't change the observables, so the observables don't constrain the lens model, or not enough. That's an illustration of how it works on the delay. So now you have 3 different mass profiles down there. That's psi of theta. And on the top, you have the arrival time surfaces for the different mass profiles. The images form at the minima, and the position of the minima don't change as a function of theta. So the lensing observable don't change. What changes is the time delay. You see the gap between the height of the bumps changes between all the profiles. So we change the time delay and not the rest, which is, of course, problematic. So to mitigate this, we go for lens kinematics. So we use kinematics of the lenses, but it's expensive. And we have 2 ways of doing this. So expensive way, you go to James Webb, obtain a 2D spectrum of your lens or of your lenses. So now we have approved time for that. So that's the ideal situation. If you don't have this, you can still use kinematic information. So you assume that's on the right side, that your lenses with time delays, so they are the green ones, and lenses without time delays are drawn from the same parent population. You measure the delays from the green guys, and you measure the kinematics from the red guys. Why? Because there you don't have a quasar that makes your life complicated to measure the kinematics. Or if you have lens supernovae, then you have the delay when the supernova is on, and then you have the kinematics when the supernova is gone. So we are not really exploring this in TD Cosmo. That's other projects. So okay, part A is ongoing. Part B is also ongoing. But we had results a few years ago, and that was H0 equals 67 with the second method on the right, with the hierarchical analysis. But we found out that the kinematics we're using for the reference samples, so the red guys here on in the circle, were biased, because we are using SDSS spectroscopy, which was fine at that time, but now with the precision we want, we found out that when you compare the SDSS photometry to Keck spectra or even James Webb spectra, they are biased by several percent for whatsoever reason. So here I have the spectra to illustrate the gain in signal to noise. So the blue ones are the SDSS. The red ones are not a smooth version of it. It's the actual, so in this case, the KCWI data. So that's Keck spectra. So we see the difference just in signal to noise, not to mention the higher spectral dispersion and better noise estimate. So in our paper TD Cosmo 4 by Simon Bire, we were presenting 2 values of H0. This one, 74, this is because now what we do is that we relax completely our mass model to capture the whole range of possible degeneracies between the mass slope and the mass sheet that you would add to compensate for the total mass in the Einstein radius. So now it's explicitly in our models. So we have the, let's say, the most possible annoying models to fit. If you do this and you apply it to the telecosmos sample, you obtain 74. So same value as before, but of course, since you introduce degeneracies, now your error bars are bigger. If you do the hierarchical analysis combining the green and the red galaxies I was showing in the previous slide, but with the wrong SDSS spectroscopy, then you get 67. So we decided to redo this analysis, so both to apply for James Webb time, to get the spectra of those guys, so that's in progress. We have the time approved for all the lenses you saw, and to redo the spectroscopy of the lenses with no time delays, but with either CEC or VLT Muse, so integral field spectroscopy. If we do this, we don't obtain 70. That's the initial value of the blinded analysis. And unfortunately for this conference, the unblinding teleconf is tonight. So I can't tell you, and I probably can't go to the afternoon session. I can't tell you the value we have now, but we will publish whatever we have tonight. So I don't know. Sorry? I have to ask the rest of the collaboration, but in principle, yes. Otherwise, why do you do this? But I can tell you tonight, no, in bars maybe, not in because this thing will last 3 hours. I'm sure, these unblinding telecons, and we may decide not to unblind if we find a bottleneck somewhere. So let's see. So of course, we find a bottleneck before unblinding, not after. Okay, so that will be so. In fact, so the paper that will be out now is improved in every respect, but the methodology is exactly the same as in the paper that published this 67. Let's see what happens. Now, just I have no time left. But I can tell you that if we do CEC spectroscopy of just one lens, this is the result we get. So remember, we had 7 lenses with simple models. That's the value we get. One lens, that's also the one I took as an example at the beginning, and a simple model, that's what we get for that specific lens. Now, if we have 7 lenses, but with a relaxed model, and using aperture kinematics to constrain a bit more the models, that's what we have. No, it's all about 70. Now you use that same lens, the model that has the whole range of possible degeneracies, and the KCWI specially resolved kinematics, that's what you get. So the expectation is that once we have James Webb NeurSpecs spectroscopy, the accuracy should be around, and precision should be around 4% per lens. So to me, that's the key thing. The hierarchical analysis, we have different opinion on this in the collaboration. I think it's fine, but you can never prove that all the lenses with time delays and no time delays are exactly from the same parent simulation, the parent sample. So that's one point we improved in the paper you will see on the web soon. So now we make sure that the red galaxies and the green galaxies in the previous slides are as close as possible in terms of observed properties, but you can't never really be sure. The best is to do the kinematics of your lenses that have time delay. So we'll do both and see what happens. Okay, just to show you some of the data, HST image of a lens, CEC IFU, NeurSpec, white light image of the same lens. That's the typical data we have now. This I already showed. That's what we call a super jackpot lens. I think this will already be fantastic just on its own, just because there are very, very few places on the source plane where you can put the source to represent this lensing configuration. So all the lens degeneracies are in fact already broken just without the lensing, the lens modeling. And when I say you can't move much the source, I'm speaking of nano arc seconds. So, it's super well constrained. Okay, conclusion. So everything is bright, blah, 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 but no, takeaway message is, for now, if you have simple models, our H0 is 74. 67, we don't know yet. We'll know more tonight. That's if you do the hierarchical analysis, but the last word will be given, I think, with the resolved, so spatially resolved kinematics of the lens for the lenses that have time delays. So check archive. At some point, there will be soon a paper with some value of H naught. So we all agreed that if H naught is -2, that's what will be in the paper. Hopefully it's not, but yeah, and that's okay. That will be my conclusion. Yeah.
So question, comments?
Actually, it's a curiosity because I don't know what is the number of the slide. You were showing the convergence profile divided by components. You basically don't need dark matter because if I can see, the red one is dark matter, but this object is only baryons, basically.
So you have the power law, which is the pink line, and the pink line is superposed with the blue line, which is dark matter plus baryons.
Yeah, but dark matter is only the red, right?
No, dark matter is dark matter is this one.
Yeah, and only baryons is green.
Yeah, so you add these two, you get the blue line, which happens to be on the power law. So you have a more complex model, and these two things kind of conspire, as we say in lensing, to give you the same profile as the simple power.
Okay, but in principle here for this galaxy, you don't need to match dark matter.
No, what you're after is the total mass. So the is supposed to capture the total mass. The other one is kind of, because I was saying you don't need to constrain the whole profile of the galaxy. Now, since you have degeneracies, one way of sorting out which are the correct ones is to keep the physically plausible ones.
Okay.
And at the moment, physics, or at least CDM, tells you that baryons plus dark matter is the correct way of representing galaxies. So if we follow this prescription, now you want to make cuts in this parameter space, the complex model, and not really rely on power laws. Now, what we do in the hierarchical analysis is to take the power law and then add the term that capture all the possible degeneracies. So we modify the power law, it's completely ad hoc. We capture all the possible mathematical degeneracies. In the end, lensing is just math. There is no physics in there.
One of the exciting things, I think you mentioned lens supernova, and I want to hear I think the combination of Euclid finding all these galaxy lenses and LSST kicking off and finding transits, that to me sounds like the numbers would just explode. Do you share that positive view?
Yeah, so actually I'm in charge of the Euclid Strong Lensing Science Working Group. At the moment, we are trying to establish some MOU with LSST to allow this. So essentially, you find lens supernovae with watch lists, and the best watch list for now will be Euclid, and probably for a long time. Also because Euclid is ahead of LSST in terms of finding the lenses. Now, there are lots of political aspects there that are very hard to handle. You have people only in Euclid, only in LSST, in both collaborations. Then you never know which rule applies to whom. If you can show the pixels to some people, but only the coordinates of the targets to some others. So we're trying to solve this mess. But obviously, yes, we need to combine the two surveys, not only for the discovery, but then Euclid has high resolution and infrared. LSST has the discovery, the time dimension, so potentially the time delays, and the colors. So no, it would be too stupid not to combine and coordinate things.
I just wanted to comment on the previous question that this is very small scale here. You're looking at 10 kiloparsec maximum.
Yeah.
And the halo around will have hundreds of kiloparsecs of size. So if you don't see dark matter here, it's nothing surprising.
Yeah, actually, all these lenses are not really dark matter dominated. We speak of a factor of 2 more dark matter than luminous matter.
So first of all, why don't you choose the best fit profile? Is that what you do, or is it just like you kind of marginalize?
Well, the thing is that no one knows the best fitting profile. I mean, you can fit perfectly a profile, but you are not sure it's any better than another profile that will fit equally well. And that's the degeneracy.
Fit the same.
Huh?
They all fit as well as the other one, basically.
Well, they can. Some will have bad chi-square, but the range of models that fit very well is big. It's too big. That's why we have bigger error bars if we don't introduce lens kinematics. So if we do the so you see these three profiles down there. They are fundamentally, they have the same analytical formula. They all fit equally well the data potentially, but they have different kinematics. So no, with well, they are bigger than with no degeneracy at all, of course, but they really shrink by a lot. Yeah, and now remember, now we don't use spatially resolved kinematics. It's just aperture kinematics. With James Webb, every pixel will be a spectrum, so you have points all over the way here.
So even with kinematics, we can find which one is the best profile?
No, you can.
Okay.
Yeah. But it's a matter of error bounds. But let's say now we know that with about 10 lenses and James Webb spectra, we will go to 1%, including the nasty effect of the MST.
Okay, so let's we thanks Frédéric again.